Welcome on this video about methods of proof. Today we are going to discuss how we are building proofs in math. First thing we need to know about math is that we are actually built on some axioms. And axioms are things that we can't prove, but we have to accept as true in order to build a house, the house of mathematics. When we want to prove something in maths, we start from these axioms and then we build the next part of our house, which are the next assumptions, etc. But humans have been around for hundreds and hundreds of years, so that we won't start from the axioms each time we want to prove something, right? We want actually to start from where the people before us left their work. So we have to start from assumptions. Assumptions are things we are thinking are true, because people before proved them starting from axioms. Where do I want to come with this? Well, in math you usually start with assumptions, and then you want to prove that some other things are true. Therefore you're building a chain. Because this is true, then this is true, then this is true, etc. In math we can distinguish 5 methods of proof: the direct proof, the indirect proof, the induction proof, and the proof by exhaustion, which you can also call in German Fallunterscheidung. It's about enumerating all the possible cases. Start with the direct proof. So you start with an assumption, and out of it you multiply, divide, inject some things you know are true in it, so that from an assertion you have a new assertion that you can form into a new assumption, and at the end, starting from the assumption, you have a direct line to B. Now there are indirect proofs. You don't start from the assumptions, but you start from not the assumptions. For example, with the contradiction. In the contradiction, we say what happens if we don't have this assumption, if the assumption is wrong. Then we come to a contradiction. Since when the assumption is wrong, there is a contradiction, therefore the assumption must be true. For the contraposition, we need to know that A implies B is equivalent to not B implies not A. So in the contraposition proof, we start from non-B, and we prove that from non-B comes not A. And since it's equivalent to this, it's true that A is true. These are the indirect proofs. Now we have the induction proof. That I'm going to explain in 1 minute. Lastly, we have the proof by exhaustion, where you just look all the possible cases. Let's look at this function. There will be 3 cases. Case x below A, the case x between A and B, and the case x greater than B. Therefore, since you have then covered this whole line, this is there, this is this part, and this is this part, you have therefore covered all possible values for x, and this is what we called the proof by exhaustion. So how do you know which one you have to use between these 4 proofs I just presented? You have to try them all and see which one works. On some problems, it won't work, so you just keep changing the proof method till you find the good one. Of course, it's not always that hard. Usually in the exam problems, all methods are pretty much the same, except for the induction proof. The induction proof, usually, it's when you want to prove something for all n's. For example, when you have sequence, n is equal something. How does it work? First, the principle of the induction proof. So it's a bit as if you had many dominoes in front of you, and you wanted to make them all fall. If you want to prove that something is true for all n's, you can prove that it's true at some point. Since it's true at some point, what you prove is if this domino falls, then the next domino will fall. Therefore, if this one falls, this one will fall, this one will fall, this one will fall. So what we actually prove is there's a point where this property works, and if it works at this point, all the domino after that will fall. And this is exactly what we are doing with the induction proof. There are three main parts in the induction proof. The start, we take an n and for it which the property is true. When we take such an n, it's true for the property when n is equal to n plus 1. So we are just proving that when a domino falls, the next one after him is also falling. Since we know the assumption is true at some point, we know there is such a point after which the domino will fall, make the next one fall, next one fall. So we know that at some point, all the dominoes will fall. Therefore, for all n, the assumption is true. For all n, careful, above the one for which it's true. It's not always the first one. Sometimes the n could be 10,000. But it doesn't matter, right? Because after that, all the dominoes for an infinite number of dominoes will fall. So the property will be true for all dominoes. Just one note about the exam. They ask us in the course to separate it in a bit more steps. So we have the Induktionsanfang, so the induction start. Then we have the Induction Voraussetzung. The prerequisite is that we take such n at which the property is true. Here I write H for hypothesis. We can also write A for assumptions. And then we say that H of n, the assumption that for n, implies that the assumption for n plus 1 is true. And this is the moment where we prove it. In German it's called Induktionsschritt. And after that we have the conclusion. So now I want you to take a blank sheet of paper and I want you to write the name of the 5 different proofs. Pause the video. Okay. Here is the answer. There are 5 proofs in our toolbox. The direct proof, then 2 indirect proofs, which are the contradiction proof and the contraposition proof. Then there is the induction proof. And lastly, there is the case exhaustion proof. Here today I'm giving you the link to the website to practice them if you need to. You have many videos about the induction and the deductive and inductive reasoning. The exercises presented in the videos are really good, so I would encourage you to try them if you are not sure about how the concept of the proof works. What can actually be difficult in this proof? Actually, most of the time, what is difficult in these proofs is things relative to sums and products. So it's not related to the proof type by itself. Therefore, if you're not confident with your ability for sums and products, I invite you to look at my other video. That's it for today. See you tomorrow for the next video about relations, functions and mapping.